Hi, my name is Mitchell Clark, and I'm one of the ESEN 325 TAs for the fall 2024 semester, and today we're going to be doing a Lab 6 hints video. So in this lab we're going to be talking all about diodes, right? And the first part to understanding about how to use them is to understand about how they work, right? So the simple way of understanding a diode is that it limits the direction of current to one direction, right? You can only go in one way, can't make the current flow the other way, right? And a diode has this symbol here, right? Where the little flat part here is to recognize that the current can't flow through this direction, right? And the way we demarcate these inputs and outputs is that we have the anode to the cathode. The current is allowed to flow from the anode to the cathode, where the anode is part of the p-type semiconductor and the anode is part of the n-type semiconductor, right? Now, how do we actually get stuff like this to work, right? Well, we got to recall back to, semiconductors and stuff. If you haven't taken ESEN 370, that'll kind of further discussion on this, but I'm going to kind of give an intuitive review about how a lot of this stuff kind of works, right? So we have our two pieces of semiconductors, right? Let's say we're just working with silicon, right? We have N-type silicon and P-type silicon. We dope these silicon metals with a couple other types of things called dopants, right? These are different elements on the periodic table, right? And for example, for N-type silicon, we put little bits of phosphorus in there, which donate an extra electron, right? So phosphorus has 5 protons, and we want to fill up its valence electron shell with 8. So we put it here in our silicon metal, and it will force itself to bond to the others to fill up its valence shell, which donates another electron into the whole metal, right? And meanwhile, we have the opposite with p-type silicon, right? So we instead add boron, which only has 3 valence electrons, and it wants to complete its electron shell, which ultimately donates a lack of an electron, or called a hole, right? There is a hole in the bonding process here, right? And these are charge carriers, right? Whenever we apply some sort of voltage across these, like the current that we're imagining, current is really the electrons themselves flowing, right? Like you're used to, current being like it flows out of the positive terminal of the battery and then goes to ground. Well, really, everything happens kind of in the opposite direction, right? And we knew this for a little bit of a while, but we were already doing everything with the convention of everything flows out of positive to negative, so we've stuck with that convention since then, right? But the electrons are what are actually flowing, and the holes can actually flow as well, where electrons can kind of move the spot that they're in, and effectively the hole can flow. But the electrons are much more mobile. And the idea is that we take these two types of pieces of silicon, the N-type and the P-type, and we smack them together, right? Two little cubes of it, right? And the idea is that, we put the two together, right? And keep in mind, one of the important things is that, like, even though we've doped it, the metal itself is still neutral, right? The silicon, like all the atoms, they're not ions, right? They're all neutral. So just putting them all together, the entire metal itself is still neutral, right? So you put the N-type semiconductor and you put the P-type semiconductor together, and they're both neutral right there, right? And then the idea is that, well, now that we have all these freely floating electrons and holes, right, and we put the two pieces of metal together, well, there's no forces or anything really keeping them in any particular spot. So eventually they start to drift across the metal, right? So some of the whole extra holes from the p-type will go to the n-type, and some of the extra electrons will go from the n-type, which will go to the p-type, right? And because of that, now there's more electrons over here and more holes over here. Now the n-type is positive, and now the p-type is negative, right? Just due to the diffusion of these different free charge carriers, right? And what ends up happening is that now, because we have a section that is positive and a section that is negative, well, if you think back to physics 207, right? Now we have an electric field between the two things, right? And because we have this electric field, a potential difference between the 2 points is going to be created, right? A voltage. And what ends up happening is that a sort of equilibrium is reached, right? Where you have the picture down here where, electrons and holes will diffuse to the other side, right? Because, there's more holes on one side and more electrons to the other. But then because they are positive and negative sides now there's an electric field going in the opposite direction to try to force things back to normal. And it reaches this sort of cycling equilibrium where the excess charge carriers diffuse. One side is positive, one side is negative, so the electric field makes them drift back to the other side and reach this equilibrium where there's about a 0.7 voltage drop between the two sides, and no current is flowing on average between the two sides. Now that 0.7 is very important. It might sound very familiar, right? Well, what happens is that if we put a diode in forward bias, right? So voltage on the anode is higher than the cathode, right? We're trying to allow current to go through the semiconductor junction, right? The PN junction. What happens is that the voltage is now going against the 0.7 volts, right? It actually shrinks this depletion region, as we call it, right? By applying that voltage, we are actively countering it. And if we apply a voltage that's greater than approximately 0.7, then the depletion region goes away, right? And now all the electrons and holes are allowed to diffuse again, to go to one side, completely unrestricted. And this means that now the flow of current is allowed to go through, right? And that's why we get that flow. And then meanwhile, if we reverse bias it, right, we try to make the cathode higher than the anode, well, the depletion region just actually gets bigger, which tries to choke that flow of current, right? So even though one side is now positive and this side is now negative, there will be trying to be some current flowing, but the depletion region gets bigger to try to counteract that, right, as best it can. So the current is about as low as it can possibly get. And this is intuitively like how this whole thing works, right? And we have mathematical representations for how this works, right? So we're given this equation right here where, ideally, if we're reversed biased, so cathode is higher than anode, the current's going to be 0. If we're forward biased, anode is higher than cathode, then the approximate current that's going through our diode is given by this equation, right? Sometimes we'll simplify things, right? We'll assume that, okay, for this diode to be on, 0.7 volts has to drop across it, and then the current will be allowed to flow, right? And a lot of these characteristics here, right, are just characteristics of the device science that would be given like in a data sheet, right? Or given to you as parameters how the device works in order to clarify a lot of these specifics, right? And it follows this sort of exponential relationship where as we increase the voltage drop across it, so here's 0, right? Once we hit about 0.5, so a little bit of current starts to flow, and then once we hit 0.7 volts, all of the current is allowed to flow, right? Because the exponential relationship just shoots up, right? But this really isn't the entire story, right? Really, we have like both sides of this plot, right? So this is if forward bias is going to be this side of the plot, right? Where the anode is higher than the cathode, right? So we increase the voltage drop across it, and once we hit this sort of point, then it's the current that goes through it shoots way up, right? And this voltage actually changes depending on the material, right? Which you can see here. But then if we reverse bias it, right, we can see a little bit of current is allowed to flow, right? Just because there is a voltage across it, but ultimately the diode tries its best to restrict it. And then, as we increase this voltage more and more and more, we actually hit the limit of what the diode can block, and we reach what we call breakdown, right? And this is the breakdown voltage of the diode, right? So looking at our picture down here, right, what ends up happening is that the depletion region gets so big that it's really trying to block all that current, but we have such a high voltage across the diode that the charges are moving like so fast. They don't even care about the depletion region anymore. They just rip through it. And because they're moving so fast, it causes permanent damage to the diode, right? So normally we don't ever want to let it get to break to the breakdown voltage, right? So as long as the reverse bias does not exceed this voltage, then it will be able to successfully block current as best as it can, right? And this is just like a basic circuit depicting that, and this is just a plot of this whole thing. And this is something that you guys will actually be doing in the lab, right? You will be asked to create this IV curve, and that's going to be done with this device. So where there's a couple different diodes that are given in your kit. This is the 1N4148, right? It's the little orange one. The cathode is the bar part stopping the current is marked by this little black bar on the end here, right? And that's the basics of just how diodes work. So now let's actually start talking about one of the direct applications of diodes that we're going to be studying in this lab, and this is the idea of a DC power supply, right? And the basic motivation, right, is that how do we get from the AC current that's in our wall down to, say, like the consistent DC power supplies that we used on our op amp, right? Or that would be supplied to any other IC that we're going to use, right? And the flow of all this follows the diagram in figure 3, right? So the idea is like you can imagine this is like one of the power supplies that are given in the lab, right? There's going to be some sort of AC transformer, right, that converts the really high current and voltage from the wall down to a much lower voltage that we're going to work with, right? And then we're going to apply what we call a diode rectifier. And this is actually given in figure 4. This is an example of a full bridge rectifier, right? And the idea is that it takes the two conduction phases, right, the positive and the negative, right, so given by like this, right, and the idea is that it tries to apply, think of it just like the absolute value of that, right, so it tries to then output it as two positive phases like this, right. And then once it's done this, we apply some sort of like low pass filter, right? Which we do with a capacitor at the output, and then this is the resistance of the load. And what it does is that this capacitor at the output holds on to some of this charge, right? Is that there's going to be a little bit of a period here, right, where the AC voltage is going to be pretty low, right? We want a consistent DC output load, right? So we attach a little capacitor there that's going to charge up once we're allowing voltage across, and then maintain that charge over the period where we're not outputting any voltage, right? So it will charge up and slowly discharge over the band, right? And then we'll be allowed to connect again, and then we'll slowly discharge again. So now the voltage at our output is much more consistent, where it hovers around a certain level, even with a little bit of ripple, right? And then we get into the idea of that, we won't really be investigating this in this class, but the idea of a voltage regulator, right? So a regulator is an even more precision device. It's going to take a semi-consistent input like this, right? This is hovering around some voltage level, right? But we don't want to deal with these like big peaks, right? A voltage regulator, like for example, a low dropout regulator, an LDO regulator, or a buck boost converter, like one that you might be studying in ECEN 340, will actually take this more inconsistent voltage and flatten it out as much as possible, right? So it might be like a little bit of oscillations like this, right? Or in the case of the LDO, it might be like even super consistent, right? And it's going to give us that really flat DC voltage that we're after, that we get to use in the lab, right? But let's focus just on the rectifier part, which still gives us our approximately DC output that we can kind of design, right? And the main ideas is that we have the two conduction phases, right? So the input AC goes high and it goes low. And whenever it goes high, right, so this shoots up, the current is allowed to flow through here into our load, into ground, right? And then it goes back through the ground, back to the AC transformer, right? You might have also seen the full bridge rectifier where the load is actually in the middle here, right? So instead of drawn like this, let's say we have the resistor in the middle like here. To me, this is a little bit more intuitive, right? It flows out here, it goes across this diode, goes through your load, and then it goes back to the transformer, right? And then on the negative conduction end, it goes down here through this diode and then back up to the top, right? And basically it's going to work on those two conducting phases where it goes through the load, it supplies the voltage to the load, goes through the ground and through the ground back to the AC line to complete the full circuit, right? And then we also have like a center tapped transformer, right? So that actually lets us reduce the number of diodes, right? Because now we get this reverse polarity that we want, right? So when VS swings high, it goes through the diode to ground, and then it's already completed because ground is stuck halfway through here in the middle of the transformer, right? But um, we don't have to deal with this specific case, right? Because what we get to end up designing in our calculations is what is effectively a centered tapped, right? We're going to input two sine waves, right, that have opposite phases like this. So they're starting at that same center voltage, so you can think of that like 0, right? And it's going to conduct, and then when this one goes high, it will go to the here, and then when this one ends up going high on its own phase, it will supply it to the V out as well. However you want to think about the voltage polarities, right? But that's the main idea about how this works. And we're given a bunch of equations to sort of classify this behavior, right? Which will be very useful for when we're going to be doing our calculations. So now this is a good opportunity to actually talk about what types of diodes are there. Well, there's many different types, right? But I'm going to talk about some of the ones that you are maybe likely to come up or encounter in many different applications or may find useful in the future, right? So obviously we have the regular diode, right, which is given in your kit as the 1N4148, right? This is just the usual 0.7 voltage drop across the diode, and it's got no particular sort of like design qualities, right? Another interesting thing is that you can actually create a simple diode like this from a BJT transistor, right? So maybe you haven't really gotten to that in class yet at the time of this recording, but the deal is that you could actually construct the BJT into what is called a diode connected state, where you connect the collector and the base together like this. And because now we have the PN junction here shorted, we actually create a usual 0.7 voltage drop diode from here, which is a nice little consequence, right? Now we also have something called the Schottky diode, right? And the deal with the Schottky diode is that it is doped where it has a little bit of a general metal here in the middle. And what happens is it actually reduces the size of the depletion region quite a bit. So now the actual voltage drop across the Schottky diode is a lot less. And this is useful for like fast switching applications, right? So if we're dealing with a much higher frequency signal input that we're trying to let pass across it, it can switch much faster, right? And then we've also got the rectifier diodes, which is given as a kit, and the 1N4006, right? This is the diode that you want to be using for building your rectifier in figure 5, right? And the deal with this is that it's just a much bulkier device, right? So it has the same voltage drop across it, right? But it can handle much more power, which is useful for what is considered to be a power supply, right? If we want to make our DC to DC or AC to DC converter, right? Then you also have the typical LED, or the light emitting diode, right? And this is constructed such that the diode is made where the dopants are picked selectively such that the band gap across them is going to correspond to a certain wavelength of light, right? And this causes them to work as an LED as a diode as you would expect, but also emit some form of light, which we understand what the use cases for that are, right? Every sort of light that we deal with in our electronics. And lastly, with the most interesting one is that we actually have the Zener diode, right? And the deal with this is that this is actually a diode that is extremely doped. It is doped so heavily that we actually use it in breakdown mode, right? Where if you remember our IV curve before, right, we never wanted to let the diode get into the breakdown region. But what we do is that whenever we dope it so heavily like this, the breakdown voltage actually becomes a much lower level. So if we have our IV curve, right, so we're used to this with the exponential relationship, right, and then we expect no current, and then it drops off like this, right? Well, we actually make it so that the breakdown voltage is much, much, much lower, and such that whenever the diode is in breakdown, it actually has consistent voltage and current qualities, right? So we place the diode in reverse bias, right? And then as long as some amount of current is flowing through it, it actually keeps the voltage, the breakdown voltage across it consistent. And this actually opens up a really useful use case where we can actually use it to sort of lock things to a certain voltage, right? Which might actually yield a sort of potential voltage regulator, which we'll talk about in an application next. So now let's talk about some of the applications of diodes, right? So we've talked about a lot of the different types. Now, when are these actually useful? So we talked about rectifiers, which are in this lab, and you learn more about those in ECEN 340 and the other power electronics courses. Those act as an AC to DC converter. We also have buck boost converters, which are a DC to DC converter, and actually uses diodes in some of the simple circuits in order to actually, in the example of the buck converter, as you see here, applies a voltage and then lowers it down to a certain level at the output. And this is investigated heavily in ECEN 340, ECEN 471, and then power electronics courses, right? Additionally, we've also got Zener diode regulators, right? And the idea is that as we mentioned before with the Zener diode, the breakdown voltage is tuned to a specific level, right? And we can put the Zener diode in reverse bias so that whenever there's current flowing through it, through the reverse bias, now the voltage across is locked to that level. We can actually clamp the output voltage to a certain level so we can effectively make a Zener diode voltage regulator, right? So we limit the current to a certain level with this series resistance, and then we let current flow through to put the diode in reverse bias and then allow the breakdown voltage to lock to this level, keeping the output voltage consistent. And this is an example of a voltage regulator, one that you might see, for example, like we mentioned up here, right? This could be a voltage regulator in question that keeps the output voltage locked to a certain level. And this is talked about in ECEN 457 and also other power electronics courses, many other types of voltage regulators, not just ones that use Zener diodes, right? Additionally, we can also create an ESD protection, right? Electrostatic discharge. Remember if we talked about, when I was talking about BJTs in one of the previous labs, when we were talking about op-amp non-idealities, these devices break, if you have electrostatic discharge coming from your body, right? And we want to prevent that. So there's much more sophisticated ESD circuits than ones like this, right? But this is an example of, let's say you apply some input voltage, right? The input voltage is always going to be within your two power supply rails. So attaching a circuit like this does nothing with normal operation. But let's say we touched the IC package, and now the VIN is going to be a gazillion volts, thanks to for the brief moment of the electrostatic discharge coming from our body. Well, now if the input voltage is really, really high above the power supply voltage, well, the diode just shorts it out and takes all that extra current to the VCC, preventing us from breaking our actual device that we care about. Additionally, we also have something in IC design called Schottky contact, right? So we talked about those Schottky diodes, right? And the idea with that is that we have a piece of metal, and then we have the two lightly doped N and P junctions, right? And what ends up happening actually is that this depiction is actually what a MOSFET transistor looks like in sort of a cross section. This is something that will be discussed later in this course. But the fundamental idea is, right, is that if we actually connect a piece of metal to a lightly doped semiconductor, a Schottky diode forms, just like the same way that it was constructed before when we were talking about it, right? We need to actually prevent this. So what we do is that we actually be sure that we connect metal to highly doped regions to produce something that we call ohmic contact, something that we prevent Schottky diodes from forming, right? And this is something that's talked about in ECEN 474 and 704 and then the other IC design classes. Additionally, we've also got oscillators, right? And the idea behind an oscillator is that it's actually an op-amp circuit such that there's no input here, right? The idea is that just in a resting condition, what it does is that it will actually produce a sine wave or some other wave output, right? This is actually kind of how signal generators work, right? And the basic idea behind these diodes, right, is that there's some sort of noise maybe in somewhere in the circuit, right? And this noise produces this positive feedback relationship, right? So the positive feedback relationship causes the voltage to go up and up and up, right? But then what happens is that because the voltage goes up, the output eventually shorts through this diode and causes the voltage to go back into negative feedback, allowing it to oscillate between two different conditions, right? And it's really interesting. And this thing that's talked about way more heavily in ECEN 457. We talk about oscillator design as well. It's a fun topic. Next, we also have mixers and demodulators, right? Mixers are the idea of frequency mixers. If I input two different frequencies into a circuit, can I synthesize another frequency? This uses lots of like Schottky diodes, usually because this is going to deal with higher switching designs. In addition, we also have the idea of a demodulator, which is if we have some sort of communication system, right? How do we actually gather the information that we were trying to transmit from our AC signal, right? This also uses diodes, similar to how rectification works almost, to remove the AC components. And this is discussed in courses like ECEN 665 and then any other sort of like communication courses. And lastly, a sort of fun application are diode logic gates. I encourage looking this up. It's an interesting use of diodes to actually create logic. So now let's talk about what you actually need to do for your pre-lab. The calculations are pretty straightforward. So we're given the rectifier circuit that we've been talking about, and then they gave us some conditions that they want our design to meet, and then we need to go ahead and design it, right? They've given us all the equations here to use. That really simplifies things. So you have the output voltage, you have the currents and everything. You can plug these components into your given equations here to determine what the capacitor and the resistor sizes or values are going to be, and then also calculate what the peak amplitude is from here. Very straightforward because they've given us the equations to use. Now, as far as the simulations go, we want to produce the IV curve for the diode given here. So we're going to sweep the input voltages and then measure what the current going through the diode is, right? Easiest way to do that is that we're going to go into multisim and build the circuit that's going to be in figure 2, and you're going to do a DC sweep from these two voltages, right? So we can go ahead and set up our simulation. So get the schematic together, go to simulations tab, DC sweep, make the source the name of the source that you provided, right? This block here that's going to be you're going to use for your DC voltage is called DC power, right? You're going to use that there. So now go to your DC sweep, set the start and stop values to what they want, make the increment tight enough so that we can get a good looking plot. Select your output as the current of the diode, and then we can go and click run. Next, it does actually say to export the simulation data to Excel and plot it. Easiest way to do that is you can go to File and you can go to Save As, and then you can export it as a CSV file instead of a .gra, which is a graph file. So export it as a CSV and then go into Excel and produce your curve and then make it look all pretty, just like the one given here in the lab manual. Now, it also says to draw the schematics for the power supply circuit in figure 5. So the simple thing is that, draw the schematic like you all are used to, put in the component values that you used. Make sure that you use the rectifier diode for the simulations and for the lab. It's the one that looks like this. And you're going to do a time domain waveform, so just add two separate voltage sources, right? Make sure that they have the same amplitude that you determined right here, and that they are in opposite phase. And then you can go ahead and run the transient simulation and measure the peak output voltage at your output. Right? So very straightforward pre-lab, easy enough. And then in the lab portion, right, you're going to be doing the exact same thing. So you're going to build a circuit, and then you're going to need to actually plot this in Excel. So you're going to need your flash drive to be able to export not the image, but you can actually export the data as well, which we'll talk about in lab. And then you also need to export it to Excel, so you're going to need to bring a computer or some other device that lets you pull up Excel or Google Sheets to actually put this together and produce that curve. And then lastly, you're also going to build the same circuit here and then go ahead and test it as before. Very straightforward stuff. demonstration just asks to see what your plot for the IV curve looks like and asks to see the correct output waveform, right? So very straightforward lab, but a lot of interesting topics.